Hello everyone, welcome to today's webinar. This is Stacy Elliott at RioSense. And today's topic, we're going to talk about how we can use viscosity measurements, specifically shear rate dependent viscosity measurements, to learn something about how proteins are interacting and then the types of microstructures that can form due to these interactions. So we're going to look at the viscosity data and try to interpret this behavior. And we're going to do this in concentrated systems. So it's going to be at the therapeutic level. So we're not going to have to worry about any changes that may occur due to the dilution process. So that's today's topic. Okay, so I want to first start off by trying to explain how we feel the viscosity measurement, particularly more extensive viscosity measurements as a function of shear rate, can fit in and really benefit the formulation process. So my circular diagram here is really looking at the formulation. We know that as you change the formulation, and in our case, our little case study that we're going to use to demonstrate this benefit, by adjusting things such as pH to adjust charge or salt type to adjust the extent of screening, we know that we can change how the proteins are interacting. And so we can regulate whether they're more or less attractive and more or less repulsive. And this interaction that exists between the proteins is going to set up the microstructure in the system. So if you're not comfortable with the term microstructure, this just means basically the placement of all the proteins throughout the formulation. And as my picture is hinting at, the systems that we are analyzing, are expected to have attractions and also expected to form clusters or aggregates. So that's the type of microstructure that we're going to be talking about today. And so as you change the formulation and you change these interactions in the microstructure that is set up, the viscosity measurement, particularly when we look at shear rate dependence, can really give you a lot of information about what's happening. You can interpret the viscosity in terms of these interactions and in terms of the microstructure that develops. So specifically what we're going to be looking at are Newtonian plateaus in the low shear region, and then this critical point where shear thinning, the onset of shear thinning occurs. And then the idea is that once you adjust your formulation, you have some expectation on how things are interacting and what sort of structures are forming. Then you can sort of confirm or deny what's happening with viscosity measurements, and then you can go back and reformulate now with more information, and you can formulate with intention rather than just doing a sort of brute force random approach. So it's really, I think, a much more efficient way, and so using this information of viscosity can be quite beneficial. So what we're going to talk about today, our case study, we're dealing with a model protein. So this is bovine gamma globulin, quite common, at a very high concentration, 250 mg per mil. And we're going to look at it under a variety of conditions. So we know its isoelectric point is somewhere close to a pH of 7. So we're going to look at it there. And then also below this, where it's going to be cationic, and higher pH where it will be anionic. And then we're going to add a variety of salts. And the idea is that we know when you add different types of salts, this changes the behavior of the protein in a different way. And generally, the reason this occurs is because it depends on how the salt is interacting with the water. More specifically, how strongly does the anions and the cations associate with water, or how strongly is this hydration layer. And then that can influence the hydration of the protein, and then also whether these salts can disrupt any sorts of attractions that are existing between the protein. So we're going to look at salt type, and then also looking at ionic strength, because that's also very clearly important as well. So that's our system that we're going to look at today to sort of illustrate how viscosity is going to fit into this process. So I first wanted to quickly review what viscosity is, because I wanted to point out a couple things of this. So many of you probably know what this is, or how viscosity is defined, but I wanted just to review a couple things. So we know viscosity is a defined property. It's the proportionality between shear stress and shear rate. And shear rate is how we're characterizing this external deformation or external flow field that we're applying. And the shear rate is essentially a velocity gradient that's perpendicular to the direction of flow. So if you look at our diagram here where the fluid in between the plates is being sheared, what we know is that when we set up the shear rate, again, emphasizing that the velocity gradient is perpendicular to flow, we know that we're basically forcing adjacent fluid elements to slide past each other. That's what the shearing motion is. And we represent this by the arrows are basically representing different magnitudes in velocity of the fluid element to sort of emphasize that. So we're forcing them to slide past each other. That's generally why people sometimes think about shear viscosity as being an internal or molecular friction. And so you can imagine that this is why viscosity is so sensitive to what's occurring on the molecular level. And this is particularly true when you're dealing with what we refer to as complex fluids. And I would put protein solutions in that category. And the complex fluid designation is really just you have generally something that would be macromolecules, so higher molecular weight, and then having a variety of types of interactions, as we discussed with the proteins, that can form complex microstructures. And so when you're doing these measurements, a single point will be beneficial, but at best it's really going to give you a general ranking of your materials and the resistance to flow. But if you look at the shear rate dependence, you're going to get quite a bit more information. And so if you look at shear rate and realize that shear rate is inverse time, has dimensions of inverse time, as we vary shear rate, what we're going to be doing is basically probing events occurring at different characteristic time scales. And we can translate those time scales into length scales with a little bit of analysis. So, looking at the shear rate dependence then, much, much more informative than a single point measurement. So I have some data here that we're going to first, just to sort of review the qualitative interpretation that you can make from shear rate dependence. And then we'll ultimately get to, the more specific. But, we're using it for proteins, but shear rate dependent viscosity can work very nicely also for colloidal systems, polymers, microemulsions, a variety of what we call complex fluids. So what we're looking at here then is viscosity as a function of shear rate. And we do have some actual data here, which I've extended with shear thinning model, the Kuroda model, because unfortunately we can't get all the way out to the higher shear rate Newtonian plateau. To do that, to get this full curve, you generally need many, many decades or orders of magnitude in shear rate. But I wanted to put this on there just so that we could discuss the whole curve. So generally what we see for complex fluids is the presence of these Newtonian plateaus, one at the low shear region and one at the high shear region. So starting with the low shear region, and this is one of the ones we're really going to focus on in today's webinar and when we analyze the data. So we want to think about why do we even have a Newtonian plateau at all at low shear rates? And the reason for this is that there's some mechanism that exists that acts to restore or maintain the equilibrium structure. Now, because we have an externally applied flow field, it will be slightly perturbed or deviated from equilibrium, but it's going to be very close to the equilibrium state in the Newtonian plateau region due to this ability on the microscopic level to resist deformation due to flow. And this restorative mechanism is going to generate a thermodynamic stress that's going to contribute to the viscosity, making the viscosity higher in this low shear plateau region. So at some point, now we have this competition really between this mechanism acting to maintain equilibrium and the shear flow that's acting to disrupt or perturb it from equilibrium. So at some point, these start to balance each other out, and we see this onset of non-Newtonian behavior. And in this case, shear thinning, and that's generally the most common case, shear thinning behavior. So what's happening is the shear flow now is overcoming this resistance, and viscosity starts to decrease as you increase shear rate. As you go higher and higher out into what we refer to as the infinite shear plateau, now we're very far from an equilibrium state. And now we've basically eliminated all these thermodynamic forces that were acting to maintain something close to equilibrium, and now it's basically dominated by hydrodynamic interactions. And if you can actually get the full range of this curve, you can basically look at the difference between the two plateaus, and those are going to give you an indicator of the degree of structure that you have due to the strength of the thermodynamic forces that you have. And it's sort of, while we're talking about this, I just wanted to point out that, you know, when we talk with customers, a lot of customers seem to think that you have to get to extremely low shear rates for all samples to get this low shear plateau. And that's not the case. The terminology is used just because of the location of the plateau relative to the high shear rate plateau. But the fact is that, and you'll see in the protein systems, sometimes the onset of shear thinning doesn't occur until say 10,000 or much greater. Actually, although not in this webinar, we have shear thinning samples that don't shear thin until over 100,000 inverse seconds. So it's really highly dependent on the system that you're looking at. Okay, so this is the general idea and the types of information that we're looking for when we start analyzing our protein samples. Okay, so now before we get into how we chose our formulation and how we chose to start adjusting how the proteins are interacting, and then also what I'm about to discuss is relevant to the interpretation, I wanted to talk about using the concept of colloidal systems to basically establish a framework for interpreting our data. So there's some resistance to trying to treat proteins as a colloidal system because they are more complex. They're not, you know, functional groups aren't uniform. They're not spherical. They're much softer. But I think that, you know, as I explain it, the general concepts from the colloidal system view can be quite beneficial and useful when we try to understand their behavior. So the first thing that, you know, is defined is the colloidal size domain. And this is going to be components ranging from about a nanometer to about a micron. So this upper bound, the micron length scale, is basically ensuring that these elements or components are small enough so that they're still undergoing Brownian motion. So thermal fluctuations in the solvent still cause this random motion on a continuous basis in the fluid. And this is important because this Brownian motion is actually one of these mechanisms that's acting to restore or maintain the equilibrium structure. So it does generate a thermodynamic stress, and it's going to impact both the magnitude and range of the low shear viscosity, but then also this critical point where shear thinning starts to occur. So keep the Brownian motion in mind. We're going to come back to that when we analyze the data. And then also the lower end of the size scale is basically to make sure that these proteins or particles, whatever you have, are significantly larger than solvent molecules and anything else that you put into the solvent, so that you can treat the solvent and its components as a continuum. And in that way, when you view colloidal systems, you view them as what they refer to as a pseudo one component system. So basically, your one component is your protein or your particle. And then you basically lump or group all of the other contributions into what is referred to as the pair interaction potential. And we'll discuss a little more about that in a moment. But the idea is that you don't have to worry about the exact positioning of everything that you put in the buffer formulation or solvent formulation. You lump that into how does it contribute to the interactions between neighboring protein molecules. And so then the other thing that I kind of hope that, you know, as we move forward with this type of analysis in protein systems is that the idea with developing these models in the colloidal area is that you want to be able to correlate macroscopic behavior to these interactions. And in our case, we're talking about viscosity behavior, but, you know, in discussions with some colleagues and collaborators, you know, the idea is that all of these protein interactions really are influencing all the other macroscopic behavior. The behavior that you observe is all tying back to the protein-protein interactions. And so this other behavior that I'm referring to are things such as solubility and phase transitions that can occur depending on the interactions that you have. And so if you start to understand how these interactions, you know, when you control the formulation, you control the interaction, you understand how that impacts your macroscopic behavior, now you can go in and, you know, you're in charge. So you know how varying some component of the system is going to change the interactions and then change your macroscopic outcome. So the whole idea is you want to start learning these things so that you can gain control and you know, intentionally formulate. And this has been quite successful in colloidal systems because the effort, you know, over time has been put in to do this. So now when I talked about the pair interaction potential and the types of microstructures that can exist based on this, so the pair interaction potential is generally looked at as, and this is phi over kT, so it scales on the thermal energy unit. And we look at this as a function of surface to surface separation, sort of defined here in our diagram, where I'm just for simplicity treating this visually as a sphere. Now the potential is used because this form is very easy to adapt to theoretical approaches. But if it's not quite resonating with you, you can also think of the force between these units is actually the negative of the derivative with respect to the separation. So in my diagram here, where I have something that has a repulsion or a positive potential and an attraction or a negative potential, you can imagine as I'm pushing the particles closer together, initially there's a resistance because I have a repulsion, but then once I overcome this barrier, now the force is attractive and acts to pull them together into this potential well. So that's sort of how to think about the positive potential being a repulsion and the negative one being an attraction acting to bring them together. So generally you won't have purely repulsive or purely attractive systems. You'll have some combination. So types of repulsions are electrostatics or even just steric repulsions, as you would force any soft molecule together. If it's in a reasonably good quality solvent, it's not wanting to be compressed. It's more of an osmotic repulsion that comes from that leads to the steric resistance. But the idea is then that you have these potential repulsions. These act as a stabilizing barrier and give you kinetic stability. So if your barrier is high enough, then for all intents and purposes, you're going to have a well-dispersed system that stays this way for some extended period of time. As this repulsion drops, and if you have this attraction, then over time, or even initially, then you can start seeing aggregation or cluster formation due to the attractive interactions. So in our case, when we deal with the proteins are known to be, in many situations, predominantly attractive to varying degrees, and known then to form aggregation or to form clusters and to aggregate. Generally, the charge level on a protein is relatively small compared to, say, a colloidal particle, and doesn't offer up too much resistance or a barrier here. So aggregation is likely and common, and this is one of the things that we want to use the viscosity to try to understand. To what extent have we aggregated our system, knowing that we don't have a huge repulsive barrier, particularly when we add salt, which can then screen it. So this is sort of the thought process and how we want to think about the proteins interacting. And I just wanted to point out that it's pretty well accepted that these attractions do increase the viscosity, and that these systems tend to be more unstable depending on the strength of attraction. But it's also true that if you have strong long-range repulsions, this will increase the viscosity also. However, on contrasting, those systems with strong repulsions are very stable because we view this as a barrier to the attraction. Okay, so this is how we're going to sort of think about the interactions between our proteins. And now for our particular system, so we have this model protein, and the first thing we wanted to do is, in some systematic way, adjust how these proteins in the formulation are interacting. So one obvious way to do this is to adjust, as I mentioned, the pH of the solution, which will change depending on the pH relative to the isoelectric point, will change the charge. But then also to further get a broader range of behavior, now we wanted to add different types of salt. So if you're familiar with the Hofmeister series, this is basically a ranking for many types of proteins. And of course, this exact ranking doesn't hold true for everything, but is valid on a number of situations. So, and we find, and as you'll see with our data, it does sort of hold to our model system. So the idea is that the position on this Hofmeister series or spectrum of anions and cations is determined by how these ions or cations interact with water. So we have the ions on top, cations on the bottom, and their behavior is actually sort of flipped. And we find that the anions are more influential. So what we're looking at then is to look at a range of either strongly hydrated or weakly hydrated anions and see how this influences our protein's behavior. So the general understanding of when you add these different types of salts to solution is that weakly hydrated salts will be more effective at salting in the proteins, meaning, so salting in is generally what we think of when we add the salt, which can associate with the surface of the protein and then potentially break up any attractive interactions between the protein that could exist. So in that way, you're reducing the attractions and therefore increasing solubility. On the opposite end, strongly hydrating ions will not necessarily associate so much with the proteins and then be less effective at the salting in, but much more effective at the salting out, which is, as you add more and more of the salt, it will detract water from the protein molecule, dehydrating it and causing it to aggregate more, essentially then increasing the strength of attraction. So we decided to pick a variety of salts falling at different points on the spectrum to see how they influence the viscosity of our gamma globulin solutions. Okay, so we do ultimately plan to fully analyze these in terms of shear rate, but let's first start off with looking at the general trend behavior of the low shear plateau viscosity. So this is that Newtonian plateau that we just identified when we were looking at the qualitative view. And just to remind you, these are high concentrated gamma globulin solutions at 250 mg per mil, and we're looking everything's at 25 C. So what we have on the right here are two plots, each corresponding to a different pH, one close to the isoelectric point of gamma globulin, the other where it would be negatively charged or anionic. And this is the zero shear plateau as a function of ionic strength, and we have a variety of salts in each pH. So looking first at the pH near the isoelectric point, the general view of the behavior here can be explained as we sort of hinted at on the previous slide. And that's that initially for all of the salt types, we see a decrease in viscosity, and then adding further salt will then cause the viscosity to increase. So this is consistent with the idea of initially salting in the protein. So we're potentially these ions are associating with the surface of the protein, breaking up some attractions that exist. So we're increasing solubility by decreasing the attractions, which is decreasing the viscosity. And then as we add more and more salt, we're now starting to take away water molecules from the protein, causing it to become potentially more attractive, decreasing solubility, and then increasing viscosity. And the effectiveness of the salt in the either salting out region or salting in region or the salting out region, it depends on where these salts fall along that series. And so what we see for each of the pHs, whether it's neutral or anionically charged, the same trend is there. On the next slide, we'll sort of focus in a little more on one of the salts and how pH causes things to shift. But before we do that, I just also wanted to point out that it is true that when we're not at the isoelectric point, so for the pH of 8.3, where we do have some negative charge, in addition to the salt potentially breaking up some attractions that exist, we can also then reduce any sort of repulsive component in the potential that exists from electrostatics by screening that. So that's another effect that comes in when you have the charged state. So then I also wanted to point out that when we look at this, we see that our particular protein, the model protein gamma globulin, does fit with this Hofmeister series. And by this I mean that the sodium bromide is much more effective at salting in than, say, on the extreme case, the sodium sulfate. So what you see is the sodium bromide both takes you down to the lowest viscosity that we can achieve by adding the salt, and then minimally changes as we add more and more salt. So it's very effective at salting in, but not so effective at salting out. So it falls on that place in the spectrum as expected. And then the opposite extreme, of course, is the sodium sulfate, where there is some salting in period at either pH, but then the increase during the salting out phase is much more extreme. And because the sodium chloride and potassium chloride fall next to each other on the series, their behavior is very similar. So, so it looks like we are, in fact, controlling our interactions by controlling the salt content and the type of salt that we're adding. And it does seem to be consistent with the idea of changing the strength of attractions mainly, reducing them initially and then increasing them as we introduce more salt. But before we further analyze these, let's just to illustrate how these do differ for the different pHs or charge strength. So what I've picked was the ones, the particular salt that showed the most extreme differences to make it most obvious. So what looking at here is the sodium sulfate and sodium sulfate at 3 different pHs. So near the isoelectric point, in a positively charged state, and in a negatively charged state. And first thing I wanted to point out is that we don't have the 0 point for the nearly net neutral state, or near the isoelectric point. We found that we couldn't get this gamma globulin completely into solution without some additional salts beyond what was in the buffer. So that's one first thing to point out, is that this near the isoelectric point, we need more salt to even get it into solution than exists in the buffer alone. Whereas that's not true in the charged state. We can easily get these proteins in solution without adding additional salt. Second thing to notice between these different responses is that the salting in region is much broader for this sample near the isoelectric point, and very narrow when it's in the charged state. So you can see then that near pH 7, it sort of reaches a minimum, above 200 millimolar, whereas the minimum occurs at most at 75 millimolar here for the charged and or the positively charged and negatively charged state. So this is one of the differences we're seeing with the change in pH. So now what we're going to do is, the idea is that as we change these interactions, this viscosity change is coming from basically the level of reversible cluster formation that you have. So we're not really able to say anything about cluster formation and the extent of cluster formation solely from the magnitude of the low shear plateau. So what do we want to do? We want to then do, as I mentioned before, these extensive shear rate sweeps, so that we can start trying to correlate this behavior to what's happening in terms of cluster formation. So this is what we've done then. So what we're going to look at here now is I've taken a handful of the formulations that we just presented the low shear viscosity for, and we did rate sweeps over as broad of a range as we could. And that's what we're looking here at this plot. So I've already, just for simplicity of viewing, because we do have a very broad range of viscosities, and it's a little hard to clearly see the shear thinning unless I've already rescaled the viscosity axis. So what I've done is I've subtracted off mu, which is the buffer viscosity, and then scaled this on the low shear plateau minus the buffer. So ideally, if I was able to get the high shear plateau, I would want to use that rather than the buffer, but unfortunately I don't have that. So this is the next best thing. And then this is still plotted versus shear rate in dimensional form. And so what we can see is, and I'll point out also, that as we go from left to right on these curves, the low shear plateau is increasing. And the other thing to point out is, so all of these samples shear thin. So we see shear thinning for all of our concentrated protein samples. And as we see from the curve, as we go from the lower viscosity solutions to the higher viscosity solutions, we see a shift to lower and lower shear rates where this critical onset of shear thinning occurs. So the shear thinning onset shifts to lower and lower rates as we increase this low shear plateau viscosity. So in a qualitative perspective, what does this mean? So you can see all the equations on the left, and we're going to go through those in a moment, but just from a qualitative view, if you didn't want to do that analysis, what is this telling you? So if you remember, we pointed out that shear rate has units of inverse time. So what that means is that when we change shear rate, we're looking at events on different time scales. And so lower shear rates are events that are occurring on longer time scales. Higher shear rates are occurring on short or fast time scales. So you can correlate, and it'll be very clear in a moment how we correlate time to length scales. But as we move then along this arrow, mainly focusing on this onset of shear thinning, we're looking at seeing an increase in this effective time scale or length scale. So this is consistent with the idea that we are getting something going from either some small clusters that we're not really sure how large they are to a much larger cluster as we move along this direction. Excuse me. So that's sort of the general qualitative view. But now how can we look at this in a more semi-quantitative way? So what we're going to do is we've rescaled the viscosity. Now we're going to rescale the shear rate and make this dimensionless as well. So how are we going to non-dimensionalize the shear rate? So we're going to think about, we talked before that we have this shear flow that we're imposing, and it's competing with some sort of thermodynamic forces that are acting to restore or maintain equilibrium. So one of these is going to be the Brownian motion, and it's going to be Brownian motion of whatever objects you have in the solution, whether they're individual units or clusters or aggregates if you prefer. And they're just diffusing around in a random manner, and this is acting to restore the equilibrium and resist the perturbation that's coming from the shear flow. So the way that we're going to non-dimensionalize shear rate is to use timescales from the Brownian motion and the shear flow to define a non-dimensional group. So the characteristic timescale for Brownian motion just comes from the idea that we're going to look at this aggregate, and we're going to say, how long does it take to diffuse a distance on the order of its size? And that's going to be our characteristic timescale of the Brownian motion. We're looking at short time self-diffusion. So this timescale comes basically just from the radius of this aggregate, which we're going to call L squared, divided by the diffusion coefficient associated with this aggregate. And we're going, because we're in a concentrated system, we're going to take basically a modified form of the Stokes-Einstein diffusion coefficient, where now we're looking at, we're going to put, instead of solvent or buffer viscosity, we're going to put low shear viscosity to account for the concentration effect. And we're going to then also include here this length scale associated with an aggregate that could be forming due to these attractions. So this is where we get the Brownian motion time. Shear flow time is more obvious. It's just inverse shear rate. So now the Peclet number is the common way of then rescaling the shear rate when you're looking at this competition of time scales. And it's just the ratio of the Brownian motion time scale over the time scale associated with the shear flow. So substituting all this in gives this equation here. So what's going to happen then is that somewhere around the point where Peclet number equals 1, these contributions are going to start becoming competitive. And so below Peclet number equal to 1, so small Peclet numbers, Brownian motion is dominating. It's able to restore the structure. Peclet number well beyond 1, now the external shear flow is going to dominate, and Brownian motion can't really make a comeback. So what we're going to do to extract our characteristic length scale of this cluster L is we're going to designate this onset of shear thinning, this point of shear thinning onset, to be a Peclet number equal to 1. And we're going to use that to extract some length scale for all of these curves, so that we can, instead of just taking a general qualitative view of this shift in critical shear rate, where now we want to actually extract some sort of value that we can compare. Okay, so that's what we have done here. So now we still have viscosity scaled in the same way, but now we have dimensionless shear rate or Peclet number. And we've chosen this length scale L for each of the samples so that the shear thinning occurs at a Peclet number equal to 1. So the first thing we see is that this does generate a very nice master curve where all of these shear responses or shear thinning portions of the curve overlay very nicely. And so now what do we want to take from this? So let's look at the actual numbers. So this is just to be fully inclusive. We have all our buffer designations here, but what I really want to focus on is the zero shear plateau and then this length scale that we were able to extract by generating this master curve as a function of Peclet number. So what we're seeing is that as low shear plateau viscosity increases, we see an increase, a consistent increase in this characteristic length scale, which we believe relates to a cluster or aggregate, is also increasing in a same trend. So this is consistent with the idea of the steady shear, low shear plateau viscosity does increase because you have this reversible cluster formation due to attractions. So presumably then as we change our buffer and we change the strength of attractions, which does change our low shear plateau viscosity, we do see this consistent change in the aggregate or cluster size that forms. So, and then also to point out, and I'll bring this point up again in a moment, but at this point in time, we're not yet ready to say that this is an absolute length scale. Right now, it's more relative. But just for reference, I wanted to point out that so with some things that are known about the gamma globulin molecules. So when we extract, say, a hydrodynamic radius from our intrinsic viscosity measurements, we get something close to 5 nanometers. And then from this particular reference here, where they've extracted radius of gyration from small angle X-ray scattering data, they saw dimensions for a monomer of about slightly more than 5, and then a dimer was about 7.6. So just to give you a relative view of what we might be looking at here with these cluster sizes. So one more way to view this, so we just sort of made the sort of grand statement that yes, what our results are indicating that this increase in viscosity that's expected to come from cluster formation does in fact correlate from the cluster size. So one of the ways that they view data for particulate systems, particulate dispersions and semi-dilute polymer suspensions is they then look at this low shear plateau viscosity as a function of essentially effective cluster volume or length scale cubed. So what we can see is that we do see a very clear correlation when we look at this on a log-log scale. So this is very satisfying. But I'll point out that there's still more that we want to learn about these systems because it's not clear what this particular rate of increase is indicating. And I just wanted to point out that when we compare our results to some results in the literature that also try to extract cluster size from the onset of shear thinning, we're seeing some differences in this rate of increase with viscosity and effective cluster volume. So ours seems to increase somewhat more rapidly, but I will point out that in our case, we fixed the gamma globulin concentration, our protein concentration, and we fixed our temperature and only changed salt content with the intent of changing the interaction strength. So it's not clear how our current studies are really looking into now. We wanted to be a bit systematic and say, okay, now we've looked at fixed concentration. Now let's see if we fix buffer, how does changing concentration impact this cluster size that we extract? How does temperature affect this for a fixed system? we kind of need to get in there and look at it in a little more systematic way to see if we can sort of clear this out. Okay, so that is what I wanted to present today. And just to summarize, I wanted to say that, despite some of resistance from people not wanting to simplify proteins and make them a colloid, I think that using that type of analysis, though, as a framework can be very helpful in interpreting protein viscosity data. And really looking at the shear rate dependence and what we can learn from this really does support the idea of cluster formation contributing to higher viscosities due to these changes in the interaction potential. And this type of analysis has the advantage over, say, light scattering or some other techniques where you have to dilute it. We're doing this in the fully concentrated state, so there's no impact due to the dilution process. And then just to point out that, we're still doing more work trying to, understand how we can make this length scale more of an absolute value, but for the moment it's still, so I would still view it as something relative at this time. So I wanted to stop there and then take a look here and see if we have any questions, which I would be happy to answer. Okay, unfortunately I got a comment from someone that some of the bottom portions of the slide were cut off. I'm sorry about that. We seem to have that problem with GoToWebinar a lot. We'll try to work to correct that in the future, but what I will say, I'm sorry about that, but you will be able to get a copy of the slides after the webinar and after the recording is generated. So sorry about that, but you will be able to see everything at a later time. Okay, so let's see. If you could just give me one moment. Okay, sorry for the pause there. I was just having some technical problems. I couldn't see very clearly the questions that were coming in. Okay, so let me quickly read. Okay, so someone is asking about the difference between concentrated samples and lower concentrated proteins. So all the data that we presented today was all high concentrated samples at 250 mg per mil. We have started to test lower concentrations of the proteins, but we're still sort of working through that data because there's a bit of a challenge there, because you will have a change in the viscosity due to just the number of proteins that are present, and then also a change in the viscosity due to the interactions and structure formation. So we have to find a way to sort of separate those out. So analyzing that situation is a little more complicated, but we're looking into that now. So someone asked a question also about what does viscosity at very high shear rate means for the colloidal framework. So I didn't talk about that too much because we don't have that data, but that high shear plateau is basically the point where the shear flow has overcome all of the thermodynamic stresses in the system that are acting to keep the equilibrium state. So those would be Brownian motion, they would be the any sort of steric repulsion or electrostatic repulsion exists. Basically, in that limit, all the stresses are dominated by hydrodynamics. So if you're not familiar with hydrodynamic interactions, it's basically just the presence of the particles. The flow field that a particle will experience will differ due to the fact that it has neighbors. And you'll have near and far field hydrodynamics. Near field is somewhat easy to understand. You can think of lubrication stresses as you're trying to force particles together, the resistance becomes very high. So hopefully that answers the question, but the idea is you go to something that's hydrodynamically dominated. Now these thermodynamic forces are nearly irrelevant, and it's a highly non-equilibrium structure state. Okay, let's see. So we have a question sort of looking at, I guess, asking if, sort of suggesting that it's not clear whether maybe a colloidal model or a polymer model is appropriate for proteins. The general trend is to use the colloidal model, which seems to fit better because the proteins, unlike polymers, don't have what I would say, for lack of a better term, degrees of freedom that the polymer does. So the polymers, or the protein rather, is not going to unfold and overlap and ultimately entangle with its neighbor like a protein does. It's more in a compact state due to the structural limitations of the protein. So the general trends look at it more of a colloid, mainly for that purpose. Is it's not really going to extend out and entangle like a high molecular weight polymer would do. Then we have a question about the instrumentation. So obviously we used our microfluidic technology, and someone asked, can we do these measurements with a rotational instrument? And I would say that potentially you could do these measurements with the rotational instrument. You would have to make sure that your particular protein or antibody that you're working with is not something that migrates significantly to the interface, because then you will have interfacial contribution to your viscosity, which is difficult to separate out from the bulk and tends to be much higher and have a distinct thinning also. So it would be confusing. And then also you'd have to, your range of shear rates would be different. So it's not clear that you would get the same extent of data from low shear plateau to well into the shear thinning regime. So potentially you could, but it's not clear exactly how that would work out in terms of range, and then also if you have any interfacial migration due to your proteins. Okay, I'll give a few more minutes just in case anyone has a question. I just wanted to point out that when you signed up, you had to submit some sort of contact information so that you can receive the webinar information. And feel free, if you didn't feel comfortable asking questions during the webinar, or if you have a thought later, please contact us and we'd be happy to discuss any questions you might have in the future. Okay, that seems to be the end of the questions. So again, thanks everyone for joining us. You will shortly see a message so that you can, if you'd like, look at the slides again, and then hopefully contact us with additional questions. Okay, thanks again. Have a good day.